Well, I think we can start. Welcome back, everyone. I was mentioning earlier that this is usually the hardest class to make it to, the one right before the spring break. So congratulations on making it. I appreciate your work ethic. But any questions, folks, to start us out? Okay, well, I don't have too many announcements today, and the recording works appropriately, so I don't think we need this one. Let's close this out. It kind of just hurts to look at. There we go. There, let me fix that window. There we go. Well, my announcements are pretty basic today. The exam 2 is due today. I mentioned I'll be emailing back in the moment I receive your exam with just a simple thank you, like with the homework assignments. But keep in mind, I also teach from now until 8:15. So if I don't get to you in a while, that would be the reason why. I'll be checking the emails tonight after my last class. Aside from that, we're moving on to finishing off. Oh, let's not scroll there. There we go. We're moving on to finishing off chapter 17. We just have a couple problems to go. Shouldn't take too much time. After that, I said if time permits, but upon further reflection, time will permit us to get into chapter 18. I don't want to get too far to chapter 18 because we're definitely splitting it across a break. So we're just going to introduce the chapter, take a look at what the new methods look like, and find a good stopping point. We'll try not to go too far into that and break a problem in half or something like that. But any questions or comments, folks, before we get started today? Okay, with the exams, I should have these graded sometime over the weekend. I gave 4 exams this week, so it's going to take some time, but probably around Saturday is when I plan to finish it all up. After that, I'll send out a mass email to the class so you'll know that grades are posted. That way you don't have to feel the urge to check compulsively like I remember doing as a student. You can just wait for the email. Well, let's get back to chapter 17. We left off on example 6, but we ought to refresh what we were even looking at for the method on this one. So here's how it begins. We have a brand new procedure, which means in this denominator for our test statistic t, we put in something called standard error. So this could just be written simply as SE, and that's it. But oftentimes I put a little bit more of a description like standard error X bar, because we're going to have different statistics there. And even in chapter 17, this formula is going to change. So all we did is we approximated the population standard deviation sigma with S. Throw it right in there using the sample data. And that's our brand new test statistic. It has a lot of ramifications. It means we're not using the normal distribution any longer. So if we're going to get a p-value, let me see if I can scroll here, it's kind of locked up. If we're going to get a p-value, we need to pay attention to the sample size because now we're using the t-distribution. Here's the method with the test statistic at degrees of freedom 29, so reduce the sample size by 1. And because this was a two-tail test, we set lower.tail to false and multiplied by 2 there. Aside from that, it's not too big of a change on the methods, except for if you have data that looks like these, the actual raw data, you might not be working with the formula directly. You might just be using RStudio, our giant calculator, to do all the heavy lifting for us. And that is appropriate for whenever you're handling data. People are not necessarily going to look up the test statistic each and every single time. We're eventually going to start automating these kinds of things. So just another reminder, if in chapter 17, if you're handling raw data and you decide to use RStudio to speed along the computation, take a look at this document right here. It's like chapter 17. I had put in an update as well just today. The one sample t procedures, I put these documents for anytime we have a new method we're using. As far as hypothesis testing goes, scroll down to this portion right here. And this describes how to handle a two-tail test, a left-tail test, and a right-tail test. Now, the modification I made was right here. It turns out you don't actually need that. If you just end your parenthesis right at that spot, RStudio is going to assume you're using the default test, which is always the two-tail test. The reason I wrote this out is I've noticed it's just a good habit to say what the alternative is every single time, because if we forget to do this, or if we never do it for a two-tail test, it becomes suddenly really easy to forget that you need this for the left-tail test, or you need this for the right-tail test when there's a greater than sign in that hypothesis. So the best practice is just always write it, and you'll never forget to put in the right description when you really want to do a left-tail test or a right-tail test. So that's our one-stop shop for hypothesis testing. We're going to use it on these data, but not in the typical way. We mentioned these data had a problem. It's actually paired data. There is not two independent samples. Every one of these observations depended on what happened in the column to the left, for the most part. And here's how you can sometimes decide you really are probably dealing with dependent data. Just wipe out a column. Now, if you look at the column to the right, you might guess, and you could be wrong on that guess, but if your guess is more often than not, that a high value here could correlate to a high value on the left-hand side, it's probably dependent data. So take a look. On the left, I have 42 this way. I would guess it's pretty high on the left right there. I know this one is 52. It's pretty high. This one is the one I think goes in a different direction. It was actually kind of low there. I just happened to guess by looking at that earlier. Take off the redacted. I had guessed wrong on both of those. This went from low to high, low to high. But generally, you have a high value. You probably started with a high value as well in these kind of data, which is a telltale sign, probably dependent. I just grabbed the two worst examples to show that case that. The better way to think about this is if they give you an identifier, this is not the variable column, just identifying patient to patient, then that's definitely indicating we used the patients twice to make the measurements. So whatever their baseline stress was here, it depends on what their stress would have been right here, 10 minutes before the surgery. So now that we know we have paired data, let's also recall what this data was all about. Every one of these values was for beta endorphin levels. They're trying to see if there is a relationship, some kind of process where beta endorphin levels might be released due to increased stress. They measured the beta endorphin levels of individuals 12 hours before surgery, where their stress is already pretty high, but their judgment was it's going to be massively higher over here 10 minutes before surgery. And so if beta endorphin levels have anything to do with stress, they might be able to see that in the blood draws that they took. So that's what the data looks like. So because they're paired, we asked, or we set mu to be the population mean difference in beta endorphin levels. We're going to take the 12 hours minus the 10 minutes. And was that a good call? Well, that's going to give us a negative value. If you took the 10 minutes values, divide by the 12 hours values, you'll get more likely positive values altogether. The good news, though, is it makes no difference. Whatever way you decide to subtract, you're going to get the same exact conclusion. Your test statistic could be positive versus negative, but everyone's p-values are the same, and so your conclusions are the same as well. So if I could do it all over again, I'd probably go 10 minutes data minus the 12 hours data. But let's stick to what we already set here, 12 hours minus 10 minutes. So we set the null hypothesis as a statement of there is no effect in the population. Beta endorphin levels have nothing to do with stress. So that's what the null is saying. And here it's saying alternatively, there is some effect. We don't know if it's going to go up or down, but there should be some effect, and we're looking for it. So that's what the alternative hypothesis is saying. We ourselves decided a high level of significance before we reject the null hypothesis at 0.01. That's really up to you if the problem doesn't specify. Typical values would be around that in the lower end, up to but not exceeding a 0.10. It'd be really weird to have alpha say like this. I think that's at the point where people are going to start to say, that is a weird choice. Why did you make that choice? You probably wouldn't want to have that kind of discussion. Well, next thing we want to do is check for conditions, which means we have to import the data and start working with it. So back to RStudio, let's get that data imported. I have it on a thumb drive, so I'll just click here from text to base. And this one is example 6. Now, this one is kind of a weird data set. For reasons I'm really not sure, something I did when I created that notepad file, something is a little bit off there. And RStudio puts the heading default to no. That's really bizarre. I don't think this ever happens in the homework. But if it does, you'll tell right away something is odd because it says variable 1, variable 2, variable 3, when it should not have said that. If you click right here, it fixes everything, and now the data is working normally. Okay, I'm not sure why this notepad file does that, but I didn't redo the notepad file because if it ever happens to you, that's the fix. This should always say yes on heading for the data that we're typically handling. Then after that, I'll have to scroll down here, click import, and there's our data. Any questions, folks, on getting your data imported so far? Okay, now that we've got it, let me just move this window just a touch. There we go. Sometimes it's a good idea to expand this out just to take a look at everything, see if it makes sense. Integer is okay there. That was the patient ID. All these are numeric is what we're expecting. And so the first thing we're going to do is this part of the problem indicated. We're going to take the difference for 12-hour levels minus the 10 minutes before surgery levels. Nice thing about RStudio, though, is that it thinks of this as a vector, and it just wants to do ordinary vector arithmetic. Think linear algebra, for example. But if you haven't taken linear algebra, and you write down this difference, or diff for short, up to you. I'll go with the shortened version. Say it gets. Call this example 6, $, and select, let's see here, we said 12 hours, so we're sticking to that. Good idea to use the up and down keys, because if I type this incorrectly, even the white space in there, I could have a syntax error just immediately. So I'll just rely on RStudio to identify the right exact expression here. Then just go minus. Same thing, example 6, $ select. Now we're taking the value at 10 minutes. And this does the pairwise subtractions across every single entry of those two vectors. Let's take a look. We have now difference gives us a 3.5 and negative 7.5. That's not a bad idea to double check we did it as intended. So let's go up here. We're taking the 12-hour value minus the 6.5 from the 10-minute value. And yeah, that would be a positive 3.5. So it tells us we're on the right track, that we have the right values when we did that subtraction. Any questions, folks, on getting the differences stored? Okay, well, let's put here, just to organize what we're writing out, this is all condition checking. And maybe one good thing to say here, now that we're talking about condition checking, is for the paired one sample t-test, we only check conditions on the paired differences. So like we mentioned before, but that was towards the end of class last time, this could be a really bad distribution, or it could be perfect, nice and symmetric, but all of that's irrelevant because we're doing a test right here on mu, which refers to the differences. So all the condition checking is now on that variable right there. So let's take a look at how bad it is. Type out hist to get a quick histogram, diff for the differences. This should always have some kind of description of what we're really looking at. You can let some of the context carry the weight. So I'll put here, just to make it brief, difference in beta endorphin levels. You could be more descriptive. You could say, as it was for the 12 hours before surgery minus the 10 minutes before surgery, but that's going to be way too long of a title potentially. It could break the graphics. So it's pretty typically, to paraphrase right here, and if you already wrote this stuff out, we already know how you're subtracting. So let's run that, and it says margins too large. If you get this kind of description here, there's a couple fixes. It's probably the title causing the problem, but also because I have a really tiny window here, just didn't want to plot it well. So let me try it once more. There it goes. So there's the histogram of the differences. And I feel like I need to rearrange these windows to make it look a little bit better. If you want to resize it, this is always a good option. Click on copy to clipboard. Then you can just make it look any way that seems appropriate. And I think we discovered you don't have to use a screenshotting tool. Let's see if this works. I think the meta file is what's causing an error in this version of RStudio. If you click on bitmap, then copy plot, come back here and just paste it in, Control V. And that didn't work either, but we gave it a try. Let me try go back here. I believe this works on other people's machines, but the one I'm running off of is not the most recent version. That's where all the weird issues come from. Let me try again. I'll go to copy to clipboard. I'm just going to use Windows Ordinary Screenshot Tool, which is Windows Shift and S, different on other machines. And this should do the job for us. So just like on your homework assignment, we have to discuss the conditions, but we have to support our conclusions as well. So this is part of the credit on your homework assignment, to support your decisions on whether the conditions are met or not, based upon this distribution right here. So looking at that, it doesn't look pretty, right? We can say that these data are, I'd say, not severely skewed or extremely skewed, but it is significant that there is a skew to these data. So I'd probably say something along the lines of these data are significantly skewed. I'll say to the left, although that's not the important part. The left skew or the right skew, same kind of problem. The issue is we're looking at a lot of skew. Now that might not be a problem. It now depends on how large was the sample size. If we have, say, 50 observations, I'd say we were in really great shape. Maybe around 30 observations, it starts to get into a gray area of we may or may not be accurate enough due to this level of skew. But in our problem, let's see what the sample size was. Once I rearrange those windows, it says the sample size is based off 19 observations, or you can look down here on the differences. There's 19 of them. So we have 19 observations. Let's write with a sample size of n equals 19, the robustness conditions are, and I would personally say not met, but I'd be really uncomfortable saying that just right here and now. If you're faced with this situation, the immediate thought is go up to the robustness conditions. They're way up there. They're somewhere up there. Let's see here. There they are. Then just take a look at where your situation falls. It says sample size at least 15. So we're on this bullet. We're not on a large sample greater than 40. And for a sample size around this range, between 15 and 40, the T procedures can be used except in the presence of outliers or strong skewness. And that's what I was referring to there. Strong skewness, well, that's what we're looking at. It's not severe, but it's strong enough to be apparent that there is skew there. Our sample size is too small to really handle that. Unless we were in this range, around greater than 40, we might have been better off. So let's go down below and say, after checking out that condition, the robustness conditions are not met. That deserves an exclamation mark because that means even if the data was collected perfectly, we truly have a simple random sample of patients, it doesn't matter. We just don't have nice enough data to handle it. So what would have the original authors done? There's some interesting people there like Tukey who are big in statistics. They would have not used the T procedures at this point. They have to use non-parametric methods. Those get a little bit wild. It's a little bit far out there for introductory statistics classes. But you should know if this happens to you, your project isn't ruined. There are still other statistical methods that can handle these data. Now, the downside is the power of the hypothesis test, when it's a non-parametric test, goes down. We can use the T procedures. The power of that hypothesis test is much higher. And that's the reason it's great when those conditions are met. And if we're going for a small sample size in our study, we should be nervous. We might be in this situation where we can't even use the original test. So what should we do in our conclusion? Well, if the conditions are not met, I'm not going to ask you to fully analyze data that we don't have the method to do or to handle. So you can always write this out. Since the robustness conditions are not met, we cannot draw any conclusions from these data using the T procedures. So that's essentially where our conclusion would end. And it feels weird to do that in a real homework problem, but that could happen in a real actual homework problem. If we made the wrong decision here, you might feel nervous. You might lose out on a lot of points potentially, but not really. If you decide the conditions were not met, so you didn't do these portions, I would just write down a comment on your paper that the conditions are met, in my opinion, here's why. And if you complete out to the rest of the analysis, I'd still give you credit for it. But you could always email me and ask, how does it look for these data? I'd be very happy to discuss it. Because again, that's a pretty pivotal thing to do. And this could happen to you as a professional later on. Someone might want you to analyze data. And if the conditions are not met, it's up to you now to put your foot down and say, I ethically cannot handle these data and give a conclusion, and here are the reasons. That's a hard thing to do, especially if you're doing contract work or consulting work, because you could be losing out on money. But for the sake of maintaining a reputation, especially in academics, I shouldn't say especially, along in the academics, that's the right conclusion to always make. Well, any questions at all, folks, so far? Okay, so this is my official conclusion. But I want to continue with this problem just to show what would you have done if the conditions were met. Let's actually analyze RStudio data just for the sake of practice with RStudio more than anything. So back over here, we know this is pretty bad data, but regardless, let's analyze it. The method is going to be t.test. And when you call that, that's going to be used for confidence intervals and hypothesis testing, whether it's one sample in chapter 17, two samples in chapter 18. So a lot of stuff goes on in this one function. The moment you call it, you should go up here and take a look at your hypotheses again, because we need some of these values. We'll begin by putting in the data. So whatever you stored right here, chuck it immediately into t.test. After that, we need to say what was the mean to be tested, the hypothesized mean. It's just designated as mu, makes sense. And we set it to 0. So it's the common value in the null, and over here again at the alternative hypothesis. Now here's where I made a change on the notes. This is a two-tailed test, which RStudio knows is the default test as well. But just for the sake of best practice, for when this is a less than or a greater than, good idea to start writing out alternative, and just pause right there on alt. It gives you some information of two.cited is what you'd put in if you have a two-tailed test. You would either put a greater or less if it's a greater or a right-tailed test or a left-tailed test. So we will do alternative equals two.cited. It has to be wrapped around with quotes because it's a string right there. And then that does the full analysis for us. So let's run that. And another issue on the plot. We try writing it again. I'll just maximize this thing and hope for the best. There we go. So we finally got our analysis. And like we mentioned before, we don't want everything here. Only include in your actual paper the portion that we're really doing as part of the analysis. If we're doing a hypothesis test, the analysis you want is all the way to right here. It produces a test statistic, negative 2.4556. Indicates the degrees of freedom, but that's probably less interesting. You don't necessarily need that because it calculates a p-value directly. Came out as a 0.02497. This portion right here is still for the hypothesis test, but it honestly doesn't really make sense to paste that in. You already know what your alternative was. This is just reminding you that that's how it computed its analysis. So I would only pull this much right here. Well, easier screenshot if you go for a little bit more. Let me try this as a screenshot. So let me put here, if the conditions were met, this would have been our next step. So Now that we have a p-value, let's take a look at our hypotheses. The significance level alpha was set pretty low at a 0.01. So coming down here, we would have said this is greater than alpha equals 0.01. So we would fail to reject the null, H naught. But that's not the right analysis. Because our data didn't even fit the procedure, that p-value is way off. It might truly be lower if we use the appropriate method, the non-parametric test. Even though it drops its power, a more accurate p-value might have given us the right information we want. But then also looking at the data again, take a note that the null was 0, which is what we're testing for. And sure, quite a lot of stuff is below 0, but there's quite a few observations, 5 people in particular, I selected 2 of them at the start of class, above 0. It looks like this problem is more nuanced than it seems. Even though there's some left leaning to it, maybe there really is no effect here, but it's going to require a lot of extra analysis and a different analysis because, well, the robustness conditions didn't even satisfy this problem. Well, any questions at all, folks, on getting through this one? Okay, well, it's a kind of a weird situation when this happens. It's not going to happen a lot in the homework. Again, just as a reminder, if you look at data that just doesn't look right like this, double check the robustness conditions, double check your sample size because that has a lot to do with it. And if you're not sure, don't hesitate to write. I'll be very happy to discuss these kind of problems. They do get pretty tricky, I'd say. Well, that was fun. Our analysis didn't get anywhere, and this is what we would have done. Let's paste this in just so we have a script for when conditions are met. And for the next problem, let's try it all over again, just to get some more practice. Any less questions or comments, folks, on that prior example? Okay, well, here's how our next one goes. This one's kind of exciting in a certain way because we've looked at this problem on day 1 of the class. Now we finally have all the tools we need to give it a proper analysis, aside from the condition checking. I don't have the raw data, and so as far as condition checking goes, there's really not too much that could be said. But you'll notice this problem is also written in a totally different style. It's parts A through G, which means this one is my attempt to show you what an exam question would probably look like. Not everything here you could do as an exam question. For example, I would have to provide this right here on exam 3. You would just have to interpret for the given p-value. Let's put here, just as a reminder, when you come back to these notes, this is a potential exam 3 type of question. Not this problem itself, but different kind of context, different data, and this type of format could be your next exam question. First thing we want to do is, well, we've seen these data before, but let's quickly read through it just to remind ourselves. We're looking at an ankle brachial index, which compares the blood pressure from your arm all the way down to your leg. It seems like it's kind of a benchmark where if something's wrong with your system overall, that's a good place to see where trouble could emerge. They say the ABI can be an indicator of different diseases, or in particular arterial diseases, and a healthy ABI is at 0.9 or greater. Worth highlighting there, that's interesting information. When they said that, a 0.9 or greater, that's something we'll compare against. So that would be the value of mu naught, the value to be tested in the null hypothesis. Oh, and let's actually give it a value. Mu naught equals 0.9. So we have an ABI for that. The next here's where the data comes in. And a study by these folks, the researchers obtained an ABI of 187 women. From here, we have a sample size, so it's a good idea to start recording these early. Makes rereading this not as tedious to have to dig these out again. They say the results were a mean ABI of 0.64. standard deviation of 0.15. Now it's kind of weird how they said this. They didn't tell us what kind of mean. They could have said population mean or sample mean. But when it says the results, it's referring to the sample of 187 women. So that would be a sample mean, which means we are allowed to write X bar equals 0.64 and S equals 0.15. Now it goes on to say, at the 1% significance level, there's a lot of recognition here. That's important too. They gave us the significance level alpha, and they also set it to a 0.01. We have pretty strong protection now from a type 1 error, but less from a type 2 error. And the question says, at the 1% significance level, do the data provide significant statistical evidence to conclude that, this is a good statement here, on average, we're talking about means, not individuals, women with peripheral arterial disease have an unhealthy ABI. We know a healthy ABI is 0.9 or greater. So if they say, test to see if we have an unhealthy ABI, this is going to be a less than direction for left, tailed test, since we have to go in the opposite direction of this 0.9 or higher. So that's our read through of the problem. Notice all the different elements we have to pick out of here just to run through the problem efficiently. But from there on out, it's not too bad to get through. We'll describe the unknown parameter. We did that on day 1, so let's just remind ourselves of what we wrote. U is going to be equal to, you could say the population mean, or the true mean, or population average, true average, whichever just flows, right? Let's go with true average this time. Let mu equal the true average. That feels weird because we're so used to saying mean. But honestly, it's not a bad word to say, and it's sometimes a good thing to say, just average as a typical word if you're giving a conclusion. So we'll say mu is the true average. We need to say ABI because these values are for an ABI itself, ABI 0.64 and ABI 0.15. So it's the average ABI for all women with peripheral, that is a interesting word, I think I got it right, arterial disease. Okay, so we've got our parameter down. Any questions so far, folks, to that stage of the process? Okay, next we'll go for the null alternative hypothesis. So H naught, always think of this as a statement that nothing is special happening to this population. This is a population of women with an arterial disease, and so nothing special happening would be, well, the average ABI should be at 0.9 or higher. Our author is always using equality here, so it always feels a little bit awkward. Our author would write this as mu equals 0.9. But if you feel like it ought to be a greater than or equals that goes there, you're right too. That's just a different stylistic choice of writing down your null hypothesis. I think it's the right choice, but I'm going with what our author typically does. Our alternative hypothesis, HA, it's a good idea to reread the question here. We want to know if we have significant evidence that on average, women with peripheral arterial disease have an unhealthy ABI. So we're asking if mu, their combined ABI on average, is less than 0.9. The last thing we can say is we're testing this at a significance level 0.01. You don't have to write it here. For part B, I'm really just looking at this and this. But if you write it down again, it's now been refreshed on the top of your mind. You'll be more likely to use this value correctly just by writing it down. We want a p-value less than 0.01 before we assume that we have enough evidence that alternative is true. Well, any questions at all, folks, to that stage? Okay, so that's our alternative. We're testing for the less than sign here. Here, just put equality or greater than or equal to 0, which really makes sense when you read that statement there. And now we're finally going through the portions that's exclusive to chapter 17. This question can be pretty tricky. But if you're in chapter 17 and you know you have one sample, it's not so bad. Any volunteers for what the degrees of freedom should be in this problem? Good call, Hannah. It ought to be 186, which would be, lost my sample size, one less than this value here. So in chapter 17, degrees of freedom are nice. In chapter 18, it goes pretty haywire. So all of this is super context sensitive, but here will be formula n minus 1 for a 186. And we'll see what happens in chapter 18 next. So let's actually highlight this just as a reminder that in an exam setting, this was really just a keyword. It's a vocabulary check in a certain sense. Nothing major happens in the formula. We just have to know it's referring to that formula when you see it. Same issue with this one. Anything that says standard error, that's also a concept checked kind of on its own. It's vocabulary in a certain sense. We have to know that it's referring to SE. But if we have one sample, this is SE of X bar. In chapter 18, the formula will change if there's two means. You would put X bar 1 minus X bar 2, and it's a whole new formula. But this one's not so bad. We just take S, divide by the square root of the sample size. Value for S is at 0.15. Divide by the root of 187 from here. And now this is the good reminder on exam 3, which is a ways out, but it's good to talk about these things early. Don't forget your calculator. It will be a real in-class exam, and we will definitely need a calculator for this one. But it won't be anything major. Any scientific calculator will do the job. So 0.15 divide by SQRT for square root 187. Honestly, this is where I make a mistake personally. Once I have a 187 here, I sometimes make a mistake and put 186 because I'm focusing on the last computation. So don't do as I did. Sometimes that won't make a noticeable effect, and sometimes it can make a pretty tremendous effect. And something went wrong there. Let me try again. Oh, it was all about those graphics again. Let me see if I can somehow fix that. Weird. Okay, now it's working. And now I have a value out. Our student is just kind of ornery today, I guess. It's getting close to spring break, so I understand. So this finally comes out to, for rounding to 4 decimal places, a 0.0110. Rounding with carry is not my favorite, but here we go. 0.0110. The rounding is really more because this is an exam setting kind of problem. If I was doing this problem, say as a homework question where I had a little bit more time, I probably wouldn't round this at all. I'd probably just use this exact value in the next computation. But if you do decide to round, no harm. This is more about the concept, less about trying to get the most accurate value possible. And the rounding here is going to give you some pretty decent accuracy regardless. Any questions, folks, on running through that standard error portion? Okay, beyond that, we need to do the test statistic. This is very similar to what you did in chapter 14 for hypothesis testing. Differences are that because it's a test statistic, we call it T as a reminder. But then it goes X bar minus the hypothesized mean, mu naught, divide by standard error of X bar. Very similar to what we did in chapter 14. The only thing that changed is the standard error. Because we're using S now, we're not assuming any value for sigma whatsoever, which is the right choice to do for these kinds of problems. So next, for X bar, we have 0.64 to plug in. Subtract the value from here. We're testing at 0.9. And that doesn't look like a very big difference until you recall what the test statistic is trying to calculate. It's taking a look at the distance between your actual data and the statement of the null hypothesis in terms of standard deviations. And that is a really small standard deviation. We had a large sample size. It is a 0.0110. And so this test statistic did look impressive to start, but now it looks tremendous when you consider the denominator. Altogether, this is going to be 0.64 minus 0.9, divide by, no harm typing that in again, but if you want more accuracy, you might have went 0.15, divide by square root, 187, and same problem as before. We widen that out, and there's our value. To 4 decimal places, this one rounds down to negative 23.7030, another rounding with carry. So negative 23.7030, that always makes me nervous. Let's see if we rounded that one correctly. You have to seriously ask yourself, though, if we misrounded here, how big of an issue is that? So 1, 2, 3, 4. I think we're okay there. But that's 23 standard deviations away. Things become unusual around the mark of 3 to 4 standard deviations. So this is like light years away from that statement here. X bar is tremendously far away from the value of the null hypothesis. So at this stage, I would still calculate a p-value. I mean, it's good practice, but it's essentially pretty much 0. It never hits 0 exactly because there's always area under the t-curve, but this has to be specified with scientific notation at this point. Let's go ahead and calculate it just for the sake of practice. It's a left-tail test, so to go this way. P-value equals probability with the t distribution. So type in PT, give it the test statistic to start, negative 23.7030. I'll put here just t to show that's where the test statistic goes in. I made this mistake last time. Let's try to avoid it this time. Next input into the PT function is degrees of freedom at 186. Because the test was a left tail test, we end the syntax right here. We don't have to specify lower dot tail as false. So that should give us our p-value. But again, it's going to look kind of funny in RStudio because we're getting something really, really small. Let me just see if I can get these windows to play a little bit better. Okay, so let's take PT, negative 23.7030, 186 for degrees of freedom. And one other graphical issue, let me widen that a little bit more. RStudio is just not very happy today. This is margins too large. Maybe I should go that way. That should correct it. And there it is. We get, I mean, we're going for 4 decimal places, but again, you have to wonder if rounding even matters here, because this is about 2.12 times 10 to the power of negative 58. This is really small in physics terms as well. That's pretty much 0. But if you're trying to get it out exactly, let's put it down here in the notes to see if we can match up values. I've got a 2.1273 times 10 to the power of, I think it was negative 58 in the order of magnitude. So the value of alpha is pretty much irrelevant, right? That is absolutely less than any alpha value you would put down in a normal statistical analysis. So say here that this is less than alpha, and we will reject H naught. So now we have a great deal of evidence that the alternative hypothesis, this one right here, is the truth about the population. Well, any questions, folks, before we now write down our conclusion? Okay. Well, we didn't check conditions, but there's a good chance the conditions were totally fine. Even if the data was skewed really, really terribly, that is a large sample size. The robustness of the t-test is going to overcome any typical skew you would see in normal data. The only thing we worry about is if the sample was random or not. But this is a serious study in the Journal of American Geriatric Society, so I would assume that they did the sampling appropriately. So our conclusion probably would go along these lines. Whenever you have a p-value where you have to use scientific notation to specify, this is a good time to say we have, let me put it on a new page. We have an overwhelming amount of significant statistical evidence that, then we'll come back. Essentially, no matter what the hypothesis test was, if your p-value is less than alpha, you're always going right here and reading out the statement with whatever mu happened to be. That's a nice thing about getting used to writing out these conditions. It's pretty formulaic after a while. It always kind of goes the same way. So down below here, we'll just say we have an overwhelming amount of statistical evidence that, here's where I'd be looking. Let's just write out what mu is. The true average ABI for all women. And it's a lot to write out all these kinds of things, but you can shorten up your description, be a little bit more terse by saying all women with this disease. At this point, that disease is in context. We've been talking about peripheral arterial disease all along. So if you shorten it up, that would be appropriate in these kinds of problems. So all women with this disease is less than 0.9. We mentioned ABI, which comes with its own package of units. But one thing that's easy to forget here is we have to mention either mean or average somewhere, because the hypothesis test is nothing to do about an individual. It's all about the averages of all individuals that happen to suffer from that affliction. But we did it, folks. That's the conclusion on this test. Any questions or comments to this stage? Okay. Well, if you did give this conclusion, people would love this result, because imagining a physician who worked with geriatrics, people who could have this condition, that's great information for them. But it's of limited value in a couple ways. Once they see a new patient, they have no knowledge of what their condition is. Their ABI could be great or bad, even if they really had peripheral arterial disease, because this whole result is just saying that on average, we can expect that the people have an ABI in the unhealthy range. But who knows what the next person is really going to look like? Doctors just would have an expectation now. The other problem, and the second problem about this is, sure, we have evidence that people with this disease are in the unhealthy range, less than 0.9. But imagine how frustrating that is if you want to treat this. You might say, well, how bad is it? What is their range on average? We didn't supply that at all. We just said it's unhealthy. The only way to get beyond that is you have to provide a follow-up analysis. A confidence interval would be your very next thing you want to do. But confidence intervals also get tricky, because if that's a left-tailed test, we would want to give a one-sided confidence interval, as weird as that sounds. It would be a confidence interval with an upper bound and negative infinity to the left. Our author happened to just not really describe those, and that's one of the reasons people like the two-tailed test right here. We would have still had the right evidence, and with the two-tailed test, our follow-up analysis would be an ordinary confidence interval, and your conclusions on the confidence interval and the hypothesis test always go directly together. However, if it's a left-tailed test, maybe not in this problem, that's a small p-value. But for a left-tailed test or a right-tailed test, your conclusion could be different based on if you're looking at the confidence interval or the left or right-tailed test. That's unfortunate in a certain sense, and that's why these tests are a little bit weird. If you did a follow-up analysis, it should be a one-sided confidence interval, which is also pretty weird on its own. Well, any last questions, folks, on the conclusions here? Okay, well, congratulations, we've done it. We essentially redid chapter 14. Chapter 14 was really just for practice, but now we're using an honest method that's used all over the place. But we have to build on it because these statistical problems are also very, very limited in a certain sense. There's just one population that we're really looking at. But what we typically see, well, not typically, but what we see often is two populations, two independent samples, and we want to test between both of them. That takes us to chapter 18. And here's how it goes. First, I want to give a preview to the notes before we just launch right into it. Like we mentioned, we're not going to try to take too much time today. One thing I want to avoid is cutting a problem like, say, this one in half. That's kind of frustrating, especially across spring break. So we'll definitely end before example 3. But here's how the procedures are going to change. First, let's look at the good news. Two-tail tests, right-tail tests, left-tail tests, they're all specified in the same exact way. We're still using the t-distribution, so we have a lot of familiarity from chapter 17. The bad news is degrees of freedom for this specific test is a little bit wild. One thing I should mention right away is we're not going to test for equal variances at all. And our author has a good reasons for why we're not doing that. We are using a specific two-sample t-test that doesn't worry about equal variances. It accounts for variances actually being different. That's one less assumption we have to worry about, and it's one less hypothesis test we have to worry about. But then the downside is the degrees of freedom are inexact, the distribution is inexact, but the test statistic that we're going to calculate is very close to a real t-distribution with that degrees of freedom. And we have a great accuracy as long as both of the samples are at least 5. So if that all happens, even though we don't have an exact t-distribution, that statement of very close becomes good enough for accuracy on p-values and accuracy with confidence intervals as well. Next thing that happens is our standard error changes radically and turns into this thing. That's the reason I get in the habits of not writing it out this way. Our author will just call it SE, but I like to think of it as a function that takes an input, like x bar 1 minus x bar 2, because that directs us to the right formula we're using and why we're using it. So to me, that's a pretty big change, and because of that, I feel it's a good idea to start right here with probability theory to describe what happened to our standard error. Well, any questions, folks, before we launch into investigating that standard error? Okay, I should mention this is going to be pretty rare. This is the one time where we just needed something out of probability theory. Some people might have already taken a probability course, which in case this might look familiar, and that's awesome. If you haven't, well, let's take a look at these results and see what they're saying. It says x and y are going to be two independent random variables. That's a random variable x bar 1, and so is x bar 2. So in this whole thing, think of the x as being x bar 1, and think of the y as being x bar 2. That's how we're going to connect this theorem here with our work down below. So we'll have two independent random variables. That's going to be equated with two independent samples that result in those random variables, x bar 1, x bar 2. The mean of x will be denoted this way, mu x. Or we could denote this as mu x bar 1 if we needed to. And let me move this window just a touch. Sorry for folks in Zoom. The mean of y could be denoted as mu y, but in our problem we could say mu x bar 2 for that one. And here's where the interesting pertinent stuff comes into play. If you take two variables, say x bar 1, x bar 2, we're more interested in subtracting between the two, x bar 1 minus x bar 2. But the theorem has the results for adding and subtracting. Take the mean of both of those variables, and all you do is add or subtract the means of the original variables. So that's pretty helpful. What's tricky now is we need a result about variance. So let's put down something as a reminder. S is the standard deviation, and if you square that, S squared would be equal to the variance. Sometimes this is written out as S equals square root of S squared, and that'd be a fine way to describe S as well, up above. So over here, we're looking at variances. And variances are pretty interesting. It doesn't matter if you're adding and subtracting. Variances are how the data varied. It's the instability of your data. and they always add up. If you have variability in X and more variability in Y, they won't subtract. Even if you're subtracting your variables, you have extra variability in the entire sum of those random variables. So they always add together. And if that's the variance, and we want to take a square root, that's the comment I was almost making here. You could also say S is square root of S squared. That's a valid formula. Everything's positive here, so no worries about pluses or minuses. Take this and square root it, and that's where we're going to get the standard deviation. Well, any questions, folks, with the run through of that theorem? Okay, so let's begin on our problem. We're not as worried about generic random variables X and Y. We're worried about specific ones. X bar 1 is a random variable in its own right, although we typically call it a statistic. And here's our setting. We're only going to be able to use this procedure if we have two independent, simple random samples. Independence means we are not in this situation. Shouldn't have closed out that file, but we can open it up pretty rapidly. So when it says we have two independent, simple random samples, what that is specifically excluding is this kind of data right here. There are two samples, but these samples are highly, highly dependent data. We measured on the same patients twice. You could redo the study as two independent simple random samples, but you would have needed 38 patients altogether, one with a measurement at 12 hours and another group at a measurement at 10 minutes. But then you'd have to wonder if that would have even made sense in this context at all. That would have been kind of tricky to make work. So when we say two independent simple random samples, we're excluding that case specifically. It specifies two sample sizes. The populations will be distributed normally. We can take that assumption off with robustness conditions once again, but we'll start that way there with assuming normality. So it says for the problem, state the sampling distributions for the following random variables. And I think for the major reason for looking at example one, it's definitely so we can get a handle on standard error. But the second major reason is it's a good reminder that everything we do comes from the central limit theorem, including the two sample procedure. We'll say here, by the central limit theorem, X bar 1, it's asking for sampling distribution. So the way we paraphrase that is with a tilde. We haven't done this in a while, so let's remind ourselves. Tilde means is distributed as. So we're saying the sample mean from the first sample, X bar 1, is distributed as normally, because the first population was normally distributed. Even if it wasn't, it would have been approximately distributed. We throw inside there the true mean, which is mu1, the true standard deviation, which is the next value, sigma 1, and that takes care of part A. Really, all we did is we cited the central limit theorem, and nothing amazing happens in part B. This is extremely redundant. Sorry about that. It's tricky though, because subscripting is not my strong suit. So let me know if my subscripts get out of whack. This distribution of X bar 2, the second sample, will also be distributed normally. But we're talking about this sample now, so we'll use mu2, then comma, go back to the second population and sigma 2. You know, one thing I should have said right here, now that I'm reading this really carefully, it says two independent samples of size n1, n2, from populations distributed this way and this way. To make that statement totally correct, I should have said right here, respectively. I think it's implied, but that word is actually pretty important. I'll be using it here and there. That's saying n1 corresponds to this one, n2 corresponds to that one, whenever we attach the word respectively in those kinds of lists. So sorry for the confusion there. But now we're ready to get to the meat of the problem. Part A was interesting. Part B is redundant after doing part A. But part C is really the whole thrust of why we're doing this first page on the notes. What we really want is the distribution of this through the central limit theorem, which means we're going to use these ideas here. Let's break it up into stages. First, we'll calculate the mean, then we'll calculate the variance, then the standard deviation. Then we'll put it all together in a statement that looks like that, just summarizing our results. Let's begin by saying the mean of x bar 1 minus x bar 2 is, referring to now part 1, and because we're doing a minus here, we'll carry the minus sign in that description. It'll be mu 1 minus mu 2. All we did is we get to these appropriate means and subtracted them. That's not too bad. But the next thing that's a little bit tricky here is, we get a green pencil. What's specified right there is not the variance, that's the standard deviation. I need to use part 2, but part 2 only talks about variances. So we have to go over here and extract the variance. So we'll say x bar 1 has variance. Take that value, sigma 1, and just square it. That's what's going on right here in that description of variance. So x bar 1 has variance sigma 1 squared. X bar 2 has variance sigma 2 squared. So from those two key components, we can now work part 2 of the problem. We're doing a minus here for mu 1 minus mu 2, and even though we're subtracting them, the variances will add up. Let's say here, the variance of x bar 1 minus x bar 2 is, take these two, just add them together, sigma 1 squared plus sigma 2 squared. That means we can now calculate the standard deviation right away at this step. All we do is we take whatever the variance was and square root it for their next step. Let's write down here, and so the standard deviation of x bar 1 minus x bar 2 is square root. Oh dear. It's almost square root of something, but I think I forgot something really super critical when we're looking at the central limit theorem. I think that's the downside of doing a class right before spring break. Anyone spot what was missing when I specified those two central limit theorems, part A, part B? To me, it's glaring, but that's because I just noticed it. It also means I need to wipe out this and this. One of those mistakes where you could just write in the correction and pretend like you never made the mistake, but there's YouTube, so it definitely happened. There's a denominator right here. Anyone recall what should be in that location? Exactly, so definitely don't forget that when you work a central limit theorem. Should be square root of n1, sample size from the first sample. Down over here, that should be square root of n2, sample size from the second sample. Then we can close those statements and go back to the pencil. Well, when we squared this first thing, I've got the numerator right, that'd be sigma 1 squared. We also square the denominator, and that will give you divide by n1. Same over here, you square that denominator, this is divide by n2. Now this statement needs some correction, let's see if we can fix that. The variance is these two components now added together. So we'll go sigma 1 squared, divide by n1, plus sigma 2 squared, divide by n2. So that's finally the right variance. Sorry for the last minute corrections on that one. So now that we have that correct variance, now we slap it with a square root. So square root that whole thing and you get sigma 1 squared over n1 plus sigma 2 squared over n2. Due to the plus right there, there's no simplification on that square root, which is unfortunate. But although it's kind of ugly, it's the right thing. here's our overall conclusion. We can say the little fancy symbol, therefore, x bar 1 minus x bar 2. Parentheses aren't needed, but it's good to think of that as one thing. It's one random variable now for which we're finding a distribution on. They'll be distributed normally. This is direct consequence of the central limit theorem. People think of it as just a new retuning of the central limit theorem. Grab the mean, it'll be mu1 minus mu2. Then grab the standard deviation, it's that thing, as ugly as it looks, sigma 1 squared divided by n1 plus sigma 2 squared divided by n2. And that's our brand new distribution. Just like in chapter 14, going into chapter 17, everything was based off the central limit theorem. But if we change what goes right here, we expect the central limit theorem to also change. It changed in an expected way. It makes sense to subtract the means. But to me, that's a pretty big surprise. This is a direct consequence of probability theory, working the variances, and the fact that there's no simplification at all through algebra. Well, we did it, folks. If that's our new distribution, everything we do, confidence intervals, hypothesis testing, it comes from there now. And also the t-distribution. A lot of other math gets us to the right places. Any questions or comments at all so far? Okay, it still doesn't explain fully how the standard error comes together. So let's make this our last portion. It says, gather 2 independent simple random samples. That's highlight worthy because if we don't have 2 independent samples, we're not using the right process. From 2 populations with unknown means, that's always a given, so it's not something we necessarily restate. It has to have unknown standard deviations. And what we'll do here is calculate the standard error of x bar 1 minus x bar 2. And we'll call it that for short. Sometimes it's referred to just as SE. Our author does this a lot. If the context, it tells you which standard error you're working on, then that's appropriate. But if you want to be specific, that's the way to say which standard error. So here's how it goes. Because of this problem, we can't really work this theorem directly. We don't know the values of sigma 1 and sigma 2. It's okay that those are unknown. That's what we're trying to estimate in the problem. But to estimate these values, we're just repeating our trick from chapter 14. If sigma 1 is unknown, but you have the data, you can just simply say sigma 1 is approximately sample standard deviation from the first sample, or just S1. Then do it again. Sigma 2 is approximately equal to S2. So we're approximating through the sample data. Then that's our standard error. We just go right here and put in SE of x bar 1 minus x bar 2 is the square root of S1 squared divided by N1 plus S2 squared divided by N2. So that's our new standard error. It's not too bad to calculate with. The nasty thing is going to be the degrees of freedom. But any questions at all, folks, on getting to that stage? Okay, well, now that we have a standard error, it goes into 2 spots. If you're doing a confidence interval, that standard error is going to go right here. If you're doing a hypothesis test, it goes under the test statistic. At this stage, essentially everything we did in chapter 17, we're just kind of redo with slightly different formulas. The conclusions look the same, setting up hypotheses all look the same. And so there's a lot of refreshing every time you get further and further into statistics. That's helpful because chapter 14 is confusing to start out. Any questions at all, folks, then, before we call it a night? Okay, definitely a good stopping point for us. I wouldn't want to go any further. We would just have to redo that work, I'd say. But when we come back from the break, this is where we'll be. Also, as a reminder, we did finish this chapter 17, so it's considered due 2 weeks away. But if you need some extra time on that one, it's understandable. We only just finished it right before a break. So if you have questions and you're working over the break, I'll be happy to help out. And it'll be due officially on the 27th, but if you need additional time, that would be just fine. Have a great one, folks, and try not to work too hard. I'll see you all in a couple weeks. Thanks, folks.
Thank you.
Yep, have a good one.
Something, fun or maybe not, work.
I'm gonna try. It's always awful to get into like a big computer game and then just put aside until May, but I might see if I can have a short game out there.
All organized.
Yeah. See ya. Yep, have a good one.